Okay, continuing with 6.3. So for example, let's solve the following. Solve the following. For all / both solutions within the interval, so within 0 to 2 pi non-inclusive. Okay, so number 1. Let's say we have cosecant inverse of 2 root 3 over 3. So once again, the first thing I want to do is always let theta, my angle, be the inverse trigonometric function. Cosecant inverse of 2 root 3 over 3. Because I can then rewrite this as normal trig function, cosecant of theta. Actually, let me write theta in purple. Is equal to the argument 2 root 3 over 3. Well, do you agree? Do you agree that I can write this as cosecant is a reciprocal to sine, so I can write this as sine of theta is 3 over 2 root 3. But 3 is really the square root of 3 times the square root of 3 over 2 times the square root of 3, which means I can reduce one instance of the square root of 3, leaving me with square root of 3 over 2. Okay, so now I'm just looking in between 0 and 2 pi without restricting to the invertible domain. Do you agree that the two places where the y-coordinate on the unit circle has a value of root 3 over 2 will be at 60 degrees, pi over 3, and 120 degrees, 2 pi over 3. So those are the two values between 0 and 360, non-inclusive, where cosecant is 2 root 3 over 3. Okay, let's do another one. So subscript number 2. Let's say we have cotangent inverse of -1. And that's a terrible inverse symbol. Let me write that better. Okay, so once again, we start off by letting theta be my inverse function. Theta is cotangent inverse of -1, which means I can rewrite this as regular cotangent of theta is equal to -1. Okay. Cotangent is cosine over sine, so I need that cosine and sine are the same, except for one of them is negative and one of them is positive. Okay, so where is that true? Well, in quadrant 2, I know that the x-coordinate or cosine is negative and the y-coordinate sine is positive, so the reference angle is 45 degrees, so that's 3 pi over 4 in quadrant 2. Now in quadrant 3, they're both negative, which would mean a positive ratio. So let's go to quadrant 4, wherein the sine is negative and cosine is positive. So the corresponding 45-degree reference angle in quadrant 4 is 7 pi over 4. So these are the two places between 0 and 2 pi where cotangent is -1. Okay, so number 3. So let's say we have tangent inverse of 0. So once again, I will let, in orange, let theta, my angle, be my inverse function. So theta is inverse tangent of 0, which is equivalent to saying tangent of theta is 0. Okay, well, because tangent is sine over cosine, I'm looking for those two angles between 0 and 2 pi, where sine, the y-coordinate, is 0, and that would be at 0 radians and at 180 degrees, or pi radians. Okay, so now let's kick it up a notch a bit. So, for example, let's find now all solutions, and I do mean all. So there's infinitely many. So find all solutions. Find all solutions to the following. So we'll either have to add plus 2 pi k, etc. So number 1. So let's say we have 6 times the square root of 3 times sine squared theta is equal to 3 times the square root of 3. So let me go ahead and rewrite this. 6 times the square root of 3 times sine squared theta is equal to 3 times the square root of 3. So the first thing I'm going to do is I'm going to divide both sides by 6 times the square root of 3, 6 times the square root of 3, 6 times the square root of 3. So I end up with sine squared theta is equal to 1/2. Okay, so now I can take the square root of both sides. So let me go ahead and move this over a bit. So when I take the square root of both sides, remember, we have to do plus or minus the square root. So I have that sine of theta will be plus or minus, well, 1 over root 2, which is really plus or minus square root of 2 over 2 when rationalized. Okay, so I have two things going on here. I have either sine of theta is negative root 2 over 2, or sine of theta is positive root 2 over 2. So in this first case, let me do theta here in purple. So in the first case, where is sine negative root 2 over 2? Well, that's going to be in quadrants 3 and 4 at the 45-degree reference angles. So that's going to be 5 pi over 4 plus 1 full revolution and 7 pi over 4 plus 1 full revolution or any integer multiple thereof. And in the second case, what color should I use? Let's use hot pink for this one. So in this second case, at what angle is sine, positive root 2 over 2? Well, that would be at pi over 4 in the first quadrant, plus any integer multiple of a revolution, and 3 pi over 4 in the second quadrant, plus any integer multiple of a full revolution. So k is an integer. It's a terrible integer symbol. There we go, much better. So that's how we write all possible solutions. Okay, so let's try another one, shall we? Okay, so number 2, what do we have here? We have 6 times tangent squared theta minus 2 root 3 times tangent of theta is equal to 0. Okay, so let's rewrite this. 6 times tangent squared theta minus 2 root 3 times tangent theta is equal to 0. So I see that there's a 2 and a tangent of theta common to both terms. So when I factor that out, what remains will be 3 times tangent theta minus the square root of 3. Is that what I get? Oh, I guess so. Okay, so using the zero factor property, I have that either tangent of theta is 0, is 0, or I have that 3 tangent of hot pink theta minus root 3 is 0. So let's solve both of these. So over here on the left, at what angles is tangent 0? Well, that's where sine is 0. So over here, theta will be 0 or plus pi k. Let me be obnoxious here. Plus, what's a period for tangent? It's pi. So pi k. So I don't really need the 0 in that case. Okay, and over here for the hot pink, so let me be thorough, where k is an integer. And over here for the hot pink, let me first solve this. So adding root 3 to both sides, I have tangent, 3 times tangent of theta is the square root of 3. And then dividing by root 3, I have the tangent of theta. Is the square root of 3 over 3. And what I'm going to do is I'm going to unrationalize that. So that's 1 over the square root of 3. So I can actually write that as 1/2 divided by square root of 3 over 2. So that I'm looking for places where sine is 1/2 and cosine is the square root of 3 over 2. That would be at pi over 6 plus pi k. But it would also be at 5 pi over 6 plus pi k. Okay, so when all is said and done, all of these are our solutions. So theta includes any integer multiple of pi, pi over 6 plus any integer multiple of pi, and 5 pi over 6 plus any integer multiple of pi, because remember, the period for tangent is pi, not 2 pi. Okay, so one more for good measure, shall we? What is this, number 3? Okay, so number 3. Before we go on to the next subsection, so let's say we have the square root of 3 times sine of 2 theta, secant of 2 theta minus 2 times sine of 2 theta is equal to 0. Okay, so let me rewrite this. We have the square root of 3 times sine of 2 theta times secant of 2 theta minus 2 times sine of 2 theta is equal to 0. So I see that there is a sine of 2 theta common to both terms. Did I leave a space in between? I did. Let me leave a space in between here. And you know what? I'm going to use, no, that's okay. I'll use orange this time. I used green last time, and that's going to upset me. Okay, so let's use orange. So we've got a secant of 2 theta common to both terms. And when we factor that out, what do we have left? Well, it looks like we have a square root of 3 secant of 2 theta minus 2. That's equal to 0. So I either have, pardon me, oh, come on, really? Okay. So we have either sine of 2 theta is equal to 0, or we have that the square root of 3 secant of 2 theta minus 2 is equal to 0. So in the first case, what's interesting, and we have to be careful here, so let me color code. I'm going to write 2 theta in purple. So 2 theta, in order for sine to be 0, must be at 0 or pi, so any integer multiple of pi. So pi times k, where k is an integer. But I'm not solving for 2 theta, I'm solving for theta. So what we want to do then is divide both sides by 2. So we get that theta is going to be pi over 2k, where k is an integer. So we're dividing by the coefficient of theta. So let's see what happens over here on the right. So adding 2 to both sides, I get that the square root of 3 times secant of 2 theta is 2. Dividing by the square root of 3, I get that secant of 2 theta is 2 over the square root of 3. And writing this upside down, cosine of 2 theta must be square root of 3 over 2. Okay, so in this case, once again, let me write 2 theta in hot pink here. I'm looking at places where 2 theta will give me cosine equal to root 3 over 2. And that's, of course, going to be in quadrant 1 at pi over 6 plus 2 pi k. And in quadrant 4 at 11 pi over 6 plus 2 pi k, where k is an integer. However, I'm not solving for 2 theta, I want to solve for theta. So I'm going to divide each of these by 2. So remember, when you divide, it just goes into the denominator. So I'm going to get that theta is equal to pi over 12 plus, forgot to divide this by 2 and this by 2, plus pi k, because I have to divide everything by 2. Or 11 pi over 12 plus pi k, where k is an integer. So altogether, what are all of the possible thetas for which this equation is true? That's going to be, let's do with the smallest, so 1 pi over 12 plus pi k. The next one is pi over 2 k. And then the next one will be 11 pi over 12 plus pi k, where k is an integer. So these are all infinitely many solutions to this. Okay, so before I continue on, I'm going to make a third video for this section.